We are recording. There any questions about anything? Any question about anything? All right. Let's continue where we were yesterday. Recall if we have x prime equal ATX with xt naught equal to x naught, then the solution is x of t equal phi of t, phi inverse of t naught times x naught, where phi of t is the fundamental matrix solution. And this last term we call the 3.2.4. Okay? So that is the solution. Now, remember, we have not taught about how to find phi of t. Well, let's take this example from yesterday. Let's take this example and let us assume, for example, x second of t minus 9, x of t equals 0. Let's take x of 0 equal minus 2 and x prime of 0 equal 4. All right. So if we look, then we got m squared minus 9 equals 0, m equal plus 1 minus 3. So we got the solutions x of t equal e to the 3t and e to the minus 3t. Okay? So knowing this, I can find the fundamental matrix. But then you say, Dr. Raful, so how good is it? Because you already know the solution. Why do you need to find the fundamental matrix? You're absolutely correct. But for now, let's do it. So let's do the transformation. X1 equal x, x2 prime, no, x2 equal to x prime. And then we will have x1 prime equal x prime is x2, and x2 prime is x second, that is 9x, that is 9x1. So we can write the system if we let x equal to x1, x2, and a is 0, 1, 9, 0, then we have x prime equal ax. Correct? Now, how do we deal with the initial condition? Okay. Now, x1 of 0 from here is x of 0, and that is minus 2. And from here, x2 of 0 equal x prime of 0, and that is 4. And so x of 0 is minus 2 and 4. And so here we have x0 equal to minus 2 and 4. All right, so we're gonna now try to find the fundamental matrix. Okay? Okay. All right. So we know the solution is 3t. So let's say for x equal e to the 3t, what do we know? We know x1 is x, x1 is x is e to the 3t, and x2 is x prime, that is 3 e to the 3t. So basically, we're gonna take phi 1 of t to be e to the 3t and 3 e to the 3t. And now, for x equal e to the minus 3t, we have x1 is x is e to the minus 3t, and x2 is x prime, that is minus 3 e to the minus 3t. Then we're going to take phi 2 to be e to the minus 3t and minus 3 e to the minus 3t. So now, phi is the columns of phi 1, phi 2. That is e to the 3t, 3 e to the 3t, and e to the minus 3t, minus 3 e to the minus 3t. There we go. Now that is the fundamental solution. So yesterday I did mess up. So I just wanted to go and revisit this. We need to be careful. Okay? But what I did yesterday works if you take the transpose of it, but we're not doing that here. So, all right. So now, so this is phi. Okay? So what is the solution in terms of the matrix? So the solution is x of t equals phi t phi inverse of 0, x0, that is e to the 3t, 3 e to the 3t, e to the minus 3t, minus 3 e to the minus 3t, times, first of all, you need to find phi 0 will be 1, 3, 1 minus 3 inverse times x0. What did we say x0 is? Minus 2 and 4. And that is your solution. Okay? Any questions? Very simple. But here we know how to solve because this is a linear problem. I mean, not only linear, it does not have solutions. Okay. So now we're going to talk about 3.24 where the matrix A is constant matrix. Okay. Oh, by the way, the principal matrix here solution is C, that is gonna be phi of t, phi inverse of 0. Since, so okay, this is by the theorem. So this is the principal matrix, which is, look at it here. Here, in this problem, the two matrix, the inverse times the matrix itself times x naught, but x naught is not part of the principal matrix. Okay? And you can see for the principal matrix psi 0 equal phi 0, phi inverse of 0 is I. This is one of the requirements of the principal matrix. It's already solved the system, but when evaluated at the initial condition, or sorry, at the initial time, its value is the identity matrix. Okay? Any questions? All right. So all right. So now we're going to look at constant matrix A. That is, we want to reconsider the system, the homogeneous system, x prime of t equal a x t, where A is an n by n constant matrix. Okay? And so what do I call this in my book? This is 3.222. So this is 3.2.22 from now on. Okay? That's the name of the equation. All right. Now, since A is a constant matrix, we are able to construct its fundamental matrix solution. Okay, let me read again. F dot M dot S, fundamental matrix solution. Everybody okay with that? Phi of T, and hence its solution. Okay, so we're gonna use enhance its solution by utilizing the eigenvalues and the eigenvalue of A and their corresponding eigenvectors. Okay, so only when A is constant matrix we can do that. All right, by looking at the eigenvalues and corresponding eigenvectors, and then we can construct the matrix and hence the solution. Any questions? Definition, and to be fair, this is definition 3.27. Are you guys reading in the book? How do you like it? What do you think? It's my typical books, but this is a little bit deeper. All right. Okay. Let A be an n by n square matrix, constant matrix, a number, lambda is said to be an eigenvalues of A if there is a non-zero vector V. A non-zero may I call n by 1, a non-zero n by 1 vector V such that AV equal lambda V. Okay? And that is 3.2.23. Okay? So this is the definition of eigenvalues, eigenvectors. Now, so from this, we have AV minus lambda V equals 0, or A minus lambda I V equals 0. And this is if and only if determinant of A minus lambda V, which is A minus lambda V, is equal 0. This is from linear algebra. Okay? This is for all vector V, for all non-zero vector V. So to determine, okay, I'll let you look at it for a second, then I'll come back to it. Okay, any questions? So hence, to find the eigenvectors, the eigenvalues, sorry, of A, we solve the equation in lambda A minus lambda I equals 0. So this notation, parallel line, mean the determinant. Okay? So in other words, what I am saying is the determinant of a dot is nothing but this one. This is the notation I'm using, okay? All right. Now, if lambda 0 is an eigenvalue of A with corresponding eigenvector V0, then we refer to lambda 0 V0 as eigenpair of A. All right? Or we can write it like this, or we can write it like this. Doesn't really matter. So we refer to lambda 0 V0 as eigenpair of A. Okay? All right. Any questions? Okay? Now, consider a solution of 3.2.22. Remember what that is. X prime equal AX. Okay? Of the form X of t equal V e to the lambda t for V belong to Rn and lambda belong to, R, but actually could be complex. All right? Then we have by differentiating X prime, we have lambda V e to the lambda t equal A V e to the lambda t. This comes from here. Okay? Now this means AV minus lambda V e to the lambda t equals 0, or AV minus lambda V equals 0, since e to the lambda t is never 0. So factoring V, we get A minus lambda I V equals 0, and this is if and only if A minus lambda V is equal to 0. So basically, what we're saying is A minus lambda I. Sorry. What we are saying is that the lambdas has to be an eigenvalue of A. So if you assume a solution like that, then your lambda has to be an eigenvalue of A. And V has to be the corresponding eigenvector, which is a non-zero. Okay? Because we have to assume V is a non-zero vector, otherwise we get the zero solution. All right. And remember, this is only works when the matrix A is constant. So we have the following theorem. Okay. This is theorem 3.2.8. Says if lambda 0 v0 is an eigenpair of A, then xt equal e to the lambda naught t v naught, which is v naught e to the lambda naught t, is a solution of 3.2.12. Okay. Now, e to the lambda 0 tv is equal to v0 e to the lambda 0 t, since e to the lambda 0 t is a scalar, not a vector. It's a scalar, okay? It's a number. So the proof is very simple. We've already proved it. Let xt equal to e to the lambda 0 t v0, then x prime equal lambda 0 e to the lambda 0 t v0, right? And that is let's say lambda 0 v0, that is lambda 0 v0 e to the lambda 0 t, because scalar is scalar times a vector, so you can write it like that. And what is lambda 0 v0? That is a e to the lambda 0 t okay, and that is let's see. So this is lambda 0 v0, lambda 0 v0. Okay, so what I wrote here, what I meant to write, this is lambda 0 I, lambda 0 v0 I, lambda 0 okay, AV equal lambda V. Oh, okay. You see, it's an eigenvalue. So this is A0 V0 e to the lambda 0 t, and not A0A, because we have AV equal lambda 0 V, because lambda and V are eigenpairs. Lambda 0 V0 are eigenpairs. Okay? And what is this? That is AX of t. So we showed x prime equal ax. So it is a solution. Okay. All right. It's very simple. I just dawned on me. I forgot to use this one. Now we have the next theorem. Just trying to give you time so you can catch up. This is theorem 3.29. Okay. Let lambda 1, lambda 2, or lambda n be distinct eigenvalues of the n by n constant matrix A, then the corresponding eigenvectors k1, k2, kn are linearly independent. I'm gonna give you 5 minutes to read the proof in the book. 5 minutes to read the proof. It's in the book. Go ahead and read it for a second. And I don't expect you to finish it or understand it all in 5 minutes, but I just want you to have an idea for our next, what comes next. Okay? Just take a look at it for a few minutes. All right. So assume the hypothesis of theorem 3.29. Then the general solution of x prime equal ax is x of t equals c1 k1 e to the lambda 1t plus c2 k2 e to the lambda 2 of t plus cn kn e to the lambda n of t, where ci for I equal 1 or to m are constant to be found using initial data. Okay, so take a look at this theorem. So remember, all the lambdas have to be distinct. And if they are distinct, automatically the eigenvectors, the corresponding eigenvectors are linearly independent, and therefore we can write the solution of the system in this form. Okay? Now, if we write phi I of t equal ki e to the lambda I of t for I equal 1 to n, then the fundamental matrix solution phi of t is formed by taking the columns of its matrix to be phi I of t, I equal 1 to n. So basically what I'm saying is phi of t is phi 1 of t, phi 2 of t, phi n of t. Okay? See, these are the columns. All right? And I'm going to do an example next. Okay? Any questions? All right. So let's take a look at an example. 3.6, we have x prime equal to -4, 1, 0, 1, 5, 1, 1 minus 1, 3 times x1, x2, x3. So here we have x is x1, x2, x3, and a is -4, 1, 0, 1, 5, 1, 1 minus 1, 3. Okay. Now, a minus lambda I are -4 minus lambda, 1, 0, 1, 5 minus lambda, 1, 1 minus 1, 3 minus lambda. Okay? This is a minus lambda I. And that is -4 minus lambda times, you plot these, times 5 minus lambda, 3 minus lambda. So this plus 1 minus, I'm going to go this way, 1 times, I'm going to cross this and that, so it will be 3 minus lambda minus 1. That's it. Okay? So we want this one to equal 0. This is a third degree polynomial in lambda that has the roots. Okay, so I'm going to find the eigenvalues. Lambda 1 equal -3, lambda 2 equal -4, and lambda 3 equal to 5. So you're going to have to simplify this and solve it. With stuff like that, I don't mind if you put it on some application and get the root. You know what I mean? So you just gotta FOIL this out, add the 1, multiply by -4 minus lambda, do this, combine it, you will get a third degree polynomial in lambda. And after you solve it, and you see they are all distinct. Okay? All right. So let K is K1, K2, K3. All right. Or let's call it K1. All right. So what we need is A minus lambda 1. Let's take it in general. A minus lambda I times K. That is A minus lambda I is going to be -4 minus lambda, 1, 1, 1, 5 minus lambda, -1, 0, 1, 3 minus lambda, K1, K2, K3 equal to 0. And what I mean by this 0, this is 0, 0, 0. This is what it means. So solving this equation, I get -4 minus lambda, K1 plus K2 plus K3 equals 0. I got K1 plus 5 minus lambda K2 minus K3 equals 0. 0 K1 plus K2 plus 3 minus lambda K3 equals 0. Okay? All right. So I'm going to come here. And I'm going to write the eigenvalues here. Lambda 1 is minus 3. Lambda 2 is minus 4. And lambda 3 is 5. So let's write them there. Okay. So these are the equation that I need to solve. So now let lambda equal lambda 1 equal minus 3. So this becomes minus K1 because lambda 1 equal minus 3. So this will be minus 4 plus 3 will be minus K1 plus K2 plus K3 equals 0. K1, 5 minus lambda is what? Lambda is minus 3. Correct? So it will be 5 plus 3 will be 8. K2 minus K3 equals 0. And I have K2 plus 6K3 equals 0. Okay? Did you check for me? Now, let's solve for K2 here. So K2 is minus 6K3. So let's put it in here. So minus K1, minus 6K3 plus K3, minus 5K3 equals 0. If I put it here, I got K1, 8K2 minus K3, minus 48 K3 did we make some mistake somewhere? Let's see. And well, let's see what we have. And 48 minus K3 equals 0. If you add them, you get K3 equals 0. Okay. So I do have a problem here. Minus 4, 1, 0, 1, 5, 1. No wonder, guys. I'm sorry. This is 1 minus 1 minus 3. Nobody corrected me. All right. So this one is 0 K1 plus K2 minus 3K3. So I'm going to have okay. So it will be minus 3 minus lambda. Okay. All right. So that makes more sense now. Sorry about that. Okay. Now, if I put lambda equal -3, I'll get 0. So we get K2 equals 0. So automatically K2 equals 0. Okay? So K2 equals 0. This equation gives me minus K1 plus K3 equals 0. And this gives me K1 minus K3 equals 0. Each gives K1 equal K3. So let K3 equal 1. Then we have K1 equal 1. So for this, we got K1 is 1, K2 is 0, and K3 is 1. You see that? Okay. Now, just a simple mistake just may give us trouble. All right. Now, let's take lambda equal to lambda 2 equal -4. Then we have -4 plus 4 is 0, K1 plus K2 plus K3 equals 0. I got K1, 5 minus lambda plus 9 K2 minus K3 equals 0. And I have, why do I have 0 K1? Yeah. And K2 minus 3 plus lambda minus 3 plus lambda equal -4 plus K3 equals 0. Okay? So this equation and this equation gives K2 or K3 equal negative K2. And this equation tells me that K3 is 9K2. So let K2 equal 1. So then here, K2 is, what is K1? Okay. No, I made a mistake here. Okay. No, that's not true. K3 for this equation, but here, K3 is equal to minus K1 plus 9K2. So if I take K2 to be 1, then K3 is -1. Then here I have -1 equal to K1 plus 9K2 plus 9, and K1 is -1 minus 9 is -10. I don't know what I got in the book. Well, I got them. So let K2 equal -1. Let's take this to resemble the book. If I take K2 equal -1, then K3 is 1. And so this will be 1 equal K1 plus 9K2 minus 9. Then K1 is is 10. It doesn't really matter. So K1 is 10, K2 is -1, and K3 is 1. You see that? I just wanted to match the book. Okay? That's all. What I had before was totally correct. Again, I just want to match the book so you know what you have in front of you. All right. Now, we have one more equation. I'm doing this in detail so you know how to do your work. So now we're going to let lambda equal lambda 3, and that is 5. So I have -4, -5, -9 K1 plus K2 plus K3 equals 0. K1 minus K3 equals 0, and K2 minus 3 plus 5 minus 8, K3 equals 0. Okay? Because lambda is 5 now. You need to be careful. All right. So from here, I'm going to get K1 equal K3, and from here, K2 equal -8 K3. Okay? So if I take, it doesn't really matter. If I take K3 to be 1, so I let, no, this one is plus. Let K3 equal 1, then K2 equal 8, and K1 is 1. Okay? So we'll have 1, 8, 1. So K3 is 1, 8, 1. Okay? All right? Okay? Now, so the general solution is x of t equals C1 K1 e to the lambda 1 t plus C2 K2 e to the lambda 2 of t plus C3 K3 e to the lambda 3 of t. And that is C1 times K1 101 e to the minus 3t plus C2 K2 is 10 minus 1 e to the minus 4t plus C3 K3 is 1 8 1 e to the 5t. Okay? Now, if we look at this as phi1, and this is phi2, and this is phi3, then the fundamental matrix phi is equal to the columns phi1, phi2, phi3, and that is e to the minus 3t 0, e to the minus 3t, 10, e to the minus 4t, minus e to the minus 4t, and e to the minus 4t, and e to the 5t, 8, e to the 5t, and e to the 5t. There is your phi, your fundamental matrix. Okay? All right? Any questions? So now what you can do is you can write, I mean, this is your solution. That's fine. That is your solution. Okay? All right? So if you want to work with this, all right, let's say you want to work with this one. Well, let's say here, this is the third order. This is the third order differential equation. So let's say we have x of 0 equal to x prime of 0, 3, x second of 0 equal to 8, 9, 11. Because I don't want any values that are here, so you can see 2, 11, 7. So x of 0, so what you're going to have to do is you're going to have a lot of work done here, okay? Either way, you're going to have to do extra work to find your solution. What you need to do is, let's say we apply this one, then you need to find x of 0 equal to 2. If you're going to put this here, this is x, and all the way. Okay, so what we're going to do is, in order to do this correctly, you're going to have to write x of t equals c1 e to the minus 3t. This is x1 of t. Okay? Because x equal to x1, x2, x3. Oh, I messed up here. So this is not correct. This is x1 of 0, x2 of 0, x3 of 0. Okay? If I'm going to have the system like that, this is the way it's supposed to be. Okay? Now, what I can do is, let's say I use this one here. So what is x of 0? So I have x of 0 is equal to all that. Is equal to C1 times 101 plus C2 times 10 minus 1, 1 plus C3 times 1, 8, 1. Okay? But what is that? What is x of 0? X of 0 is 2, 11, and 7 equal to that. So that means 2 equals C1 plus 10 C2 plus C3, 11 equal to minus C2 plus 8 C3 and 7 equal to C1 plus C2 plus C3. So you need to solve for C1, C2, and C3. You see what you need to do? Okay? Are you with me? On the other hand, if we use the fundamental matrix to write the solution, then x of t equals phi of t, phi inverse of 0, x 0, and this is phi of t, phi inverse of 0 times 2, 11, 7. And that is, you have to have this matrix here, e to the minus 3t, 0, e to the minus 3t, 10 e to the minus 4t, minus e to the minus 4t, e to the minus 4t, and e to the 5t, 8 e to the 5t, and e to the 5t. Okay, so this is phi. Times phi inverse of 0. Phi 0 is 1, 0, 1, 10, minus 1, 1. Okay, and 1, 8, 1 times 2, 11, 7. And that is the inverse of that matrix. And then you're done. So you can do the solution like that, or you can plug in and find C1, C2, C3. Okay? And you should both get the same answer. No book tells you that, but I like to explain things because usually students get lost between writing the solution in terms of the eigenvalue, eigenvector, and in terms of the fundamental matrix. So now you see both sides, how it works out. Any questions? Okay, I'm gonna stop here, and tomorrow we're gonna learn how to find, we are already learning how to find the fundamental matrix, but tomorrow there is a concept called the exponential matrix solution, and we're gonna learn how to find it. We'll do that tomorrow. I'm gonna stop here. My back is killing me today. Okay? Considering how fast I go, I still cover what time and a half of what other professor covered in this time. All right. Any questions?
I just had a couple quick questions of going over like the exam upcoming on Saturday. What
Yes, sir.
chapter is it gonna be over?
It's gonna be over up to what I do tomorrow, and I will do a nice example, or I don't have to include tomorrow, up to today. So basically, if you've been doing your homework similar to the homework, similar to the lecture I've been doing.
Okay.
Note
And then is it like for the exam, is it gonna be like open book, open notes, or is it
it's open everything
okay?
except AI and your friends.
Gotcha. Thank you.
All right. Yeah, it's open book. Open note if you're taking notes, whatever you want to do, just don't use other people or AI. I mean, if you're going to use AI to find the eigenvalues for this one, that's fine. I really don't care. You know what I mean? But make sure they're correct. Okay? Any other questions? Other questions? All right. Tomorrow I'll tell you when I'm going to pause the exam, Saturday or Saturday, Sunday, or Friday, Saturday. All right? Or if I can, I may do it Friday, Saturday, Sunday. You choose a date. How's that? I may do that, but I need to figure it out how it's done. All right? I've never done it like this before. Okay. I will see you tomorrow.